Hi, I'm Przemek Chojecki, PhD in mathematics, running UlamAI, an AI mathematics company where actually we build products around formalization of mathematics. And in this video, I'm going to talk to you about our product UlamAI, which is an open source autoformalization, but also about how interesting times we're living in when it comes to research. Because thanks to GPT 5.2 as well as Opus 4.6, which are the recent models from both Anthropic and OpenAI, we're currently going through the Renaissance period, and it's only going to get much better. Because basically those models are good enough to provide you with really new insights, or at least give you such a broad spectrum of literature already in a particular research field that it allows you to find new connections, prove new theorems, have new insights into the old problems. This is what's happening actually with some of the Erdős problems. So if you haven't heard Erdős problems, first of all, Paul Erdős was very prolific Hungarian mathematician. He went basically from country to country, from conference to conference, speaking with a lot of mathematicians. Then there's an Erdős number for that reason, meaning how far away you are from Erdős when it comes from collaborating. If you have a paper written together with Paul Erdős, you have Erdős number 1. If you have a paper with someone who has written a paper with Erdős, you have Erdős number 2, and so on. I think my Erdős number is like 4. So I have written a paper with someone who has written a paper, has written a paper with someone who has written a paper with Paul Erdős. So that's already cool. But basically, if you're in mathematics, if you have any kind of collaboration, you will have a non-zero Erdős number. He was such a prolific mathematician that he created literally, I think, over 1,000 papers, and there are many with different conjectures. So this particular website run by Thomas Bloom is actually trying to get them all together in a very nice form. You have all the tags, and at some point what really started to happening, this is a great text by Kevin Barreto, which was actually one of the people deeply engaged here. He's, I think, a student at Cambridge. He managed to prove some of the problems thanks to AI, especially problem 7 to 8 was one of the non-trivial examples, because there are also trivial examples. So he managed to prove those problems thanks to AI. You can see all that on a forum here. Problem, then it was also proved in Lean. Lean is a language that allows you to verify correctness. Even if you don't understand the proof, this is how machines can read and verify the correctness of the proof. So that's cool. So you can do it here. And as you can see, there are 84 comments about this particular problem because there's a lot of people engaged in that. So that was a very cool example, and this is what's already happening. Of course, the bar is increasing in a way that people are saying, okay, this wasn't that hard, this wasn't novel. Basically, the techniques used for that were found elsewhere, but it's actually happening across the board. You can we already started seeing that in other sciences. Maybe it's not yet groundbreaking results, but you're definitely getting a help. You're definitely getting AI to give you non-trivial insights, make your work as a researcher much faster. And this is what this is about. So this is also why I started and why I directed AI in this direction, because what I care about is solving mathematics in order to solve AI, in order to solve science, because I believe that we're going to live through this Renaissance period. And for that to happen, we need to make sure that, research, we're going to definitely make it much faster. That's sure for now. This is nothing controversial. If you worked with models like GPT 5.2, especially extended thinking in pro version, who can think for over an hour, you're going to be amazed by the capabilities. However, those models still hallucinate, and on top of that, they are not really that good at verification, or at least they can verify themselves if you guide them, but there's a lot of prompting back and forth. In order to make really great stuff with boosting research, what we need to do is have some kind of autoformalization in order for machines to verify themselves, so that they can do research, verify that this research is correct, and then keep building on that, because that's how research is being done in any field. This is a very cumulative activity, very social one as well. This is an aspect that people keep forgetting about mathematics as well, is that it's not enough for you to convince yourself that you have a proof of a new theorem. You have to convince others. You have to convince, for example, reviewers at a journal, because usually this is how the process works. You have something that you deem new, you write that down, and then you send that to a journal in order for that to be verified by other mathematicians, because the proof itself is nothing without others accepting that, without others saying that this is fine. But for machines, in order, because we're going to have so much more research, some of that of course will be totally worthless and not interesting, but we have to also sift through that, and in order to sift through that quickly, we need other machines to keep doing the job. So this is where UlamAI comes into the picture. This is basically what I'm interested in, having this kind of auto-formalization, because that also will allow to do research not only in mathematics. Mathematics is just the core, but you can go far beyond that and also make sure that AI is getting better, because you'll be able to have architecture searches, for example, for better implementations of LLMs, for better quantization, so making sure that the compression that you're getting, putting on models is much better than you had previously, and you'll be able to do that much faster because you won't have to run experiments. You will be able to deduce that from a general theory. That's the goal here. And of course, this verified reasoning goes beyond just mathematics and AI. You can apply that in, for example, stuff like evaluation of agents, evaluations of the cloud infrastructure, chips, verified also on different SEC filings in finance. There's the whole domain on formal finance. This is really cool stuff that can happen here. And it's especially important if you want to make sure that you have LLM output being formally verified, because this is what this is about. So you have an LLM, they can hallucinate, they can be imprecise, but you have to you want to force them in a way or verify that the output is really going into this particular direction. So this is also very true, for example, for pharma industry, where you will have to be very precise. Medicine as well. There's a lot of applications of that kind of formal reasoning and why it's important. In mathematics, there's a language called Lean, and currently if you go with UlamAI, also I invite you to install that. You can start trying to prove things or formalize from tech directly. So the Lean language allows you to basically have something that is machine readable. This is a different language. You can think about that. This is a programming language that allows you to write mathematics in a formal way. And basically what UlamAI is doing is you plug in your LLM. You can plug in Codex from OpenAI, Gemini CLI, you can plug Claude Code, and basically allow that to go back and forth with Lean in order to produce a formalization of a theorem. And of course, that kind of process is generalizable to other domains as well. So I think that's pretty cool. And this is what I'm working on as well. So everything here is open source. If you have any comments, let me know here on the video under the comments, or just reach out to me on LinkedIn, Twitter. I'm pretty active. And of course, I'm going to revive the channel on this YouTube channel, but also different my Substack and other places to really show you along the way. I'm working with a lot of agents right now, mostly Codex from OpenAI. I think that's from code precision, that's much better from my perspective, and especially for doing much harder stuff. Claude is a little bit faster, but it's often less efficient when it comes to what it produces. So I prefer Codex, but I'm working with both. Gemini a little bit less. I use it sometimes on the web to verify some of the output, so I think that's cool. And of course, I'm testing some open source models with Ulama to make sure that everything works fine with UlamAI here. But there's going to be a lot of things along the way. I'm going to build that, but also have fun with other models. So definitely stay here on the channel for additional content. For now, I'm going to invite you to start using UlamAI if you haven't. There's going to be full-fledged tutorials for how to install it, how to run it, what you can do. Also, what I plan to add on to UlamAI is for people who are little less versed in mathematics, an automatic way to actually convert your tokens into interesting science, because I think that's also would be very interesting to you can, for example, have a lot of Codex tokens, but you don't know where to spend them. In a way, you don't know what to build at the moment. So maybe you want to prove some open mathematics. I think that's a pretty cool application. So I'm going to add that as well, or maybe this will be either add-on on top of UlamAI or maybe a separate repository. We're probably going to build that on the channel as well. So yeah, thank you for watching. Subscribe to the channel, as I've mentioned. I'm going to build very cool stuff here and invite you all also to join me. This is an open source process and we're going to build very cool stuff. Thank you for watching.